everyone. This is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So, in this session, I will explain how to solve problems of springs. So, already previous session we have discussed about springs topic, helical springs and torsional springs and closely coiled helical springs. So, some more problems I will explain in this session. The first problem on safety valve. So, here the given problem is a safety valve of 60 mm diameter is to blow off at a pressure of 1.2 Newton per mm square. So, here you are designing the spring for safety valve. So, here safety valve diameter 60 mm diameter is given and its pressure, the blow-off pressure of 1.2 Newton per mm square. It is held on its seat by a closed coiled helical spring. The type of the spring is here closed coiled helical spring. So, the maximum lift of the valve is 10 mm. So, the lift of the valve is 10 mm. So, it is nothing but the deflection of the spring. Design a suitable compression spring of spring index 5. So, design a suitable compression spring of spring index is 5 and providing an initial compression of 35 mm. So, here, we are providing initial compression 35 and the spring index is 5. So, and the maximum lift is 10 mm. So, here you have to design the spring for a safety valve. The maximum shear stress in the material of the wire is given 500 megapascal. The modulus of rigidity, that is CRG, the spring material is 80 kilonewton per mm square. The first step is for any problem, how to write the given data. So, here given some take walls factor is 4C minus 1 by 4C minus 4 plus 0.615 divided by C is given. The walls factor formula. If not given, we have to calculate. So, here what he has asked data in design part, diameter of the spring wire and mean coil diameter wire and number of active turns and pitch of the coil. So, diameter of the spring wire. So, this is first one is D and mean coil diameter capital D and number of active turns N. Total turns are different and number of active turns are different. So, already we have covered in theory part and pitch of the coil. The first step is given data. So, the given data is the given data is the valve diameter is 60 mm and the maximum pressure is 1.2 Newton per mm square and here delta 2 is the compression of the spray valve. So, the maximum lift of the valve is 10 mm and C is 5 and delta 1 is 35 mm. This is initial compression is 35 mm and shear stress is 500 megapascal. So, we convert into 1 megapascal is equal to 1 Newton per mm square. So, that the 500 megapascal is equal to 500 Newton per mm square. So, G is 80 kilonewton per mm square. Convert into Newton per mm square. 80 into 10 cube. The first first one is diameter of the spring wire. That is a small d. So, how do you calculate the wire diameter? We will see in this procedure. First, let's take the diameter of the spring wire is small d. So, you know that the maximum load acting on the valve, which it just begins to blow up, the blow up pressure is given So how much given the blow pressure? The blow pressure is 1.2 in Newton per mm square. So pressure you know, clear, and the area of the valve you can calculate. So why? Because here diameter of the valve is given. The diameter of the valve is 60 mm. Clear. So that the load acting on the valve. So by using pressure formula, so pressure is equal to load upon area. So here the load is the maximum load, and the area of the valve is A is 5 by 4 into D square. So D already given the 60. So substitute in this area formula and then find out W. So here calculated the W is 3394 newtons. So that is 3394 newtons. And the maximum compression of the spring. So here two compressions are there. So the one is initial compression and the maximum lift. So initially the compression is 35 mm. Initially 35 mm. So the total deflection is, so initial compression plus maximum lift. Clear. So this initial compression or deflection. So in this the problem given, the initially the delta 1 is 35. Delta 1 is 35 and the maximum lift is 10. So total 45 mm. The load is 3394 newtons. So this load is set by providing initial compression of 35 mm. So that the maximum load on the spring when the valve is open, that is for maximum compression. So what is the load? Need to calculate. For 35 mm compression, so already we calculated that load is 3394. For maximum compression of the spring, so what is the load? So the maximum compression is here total 35 mm, 45 mm, 35 plus 10. At this compression, so what is the load? So again calculate the load is equal to, here load already you calculated this 3394. So at 3394, so what is the compression? 35. So at 45 compression, so what is the load? So we'll explain now clearly here. Here, take this load. This load is for at 3394 newtons. The compression is 35 mm. Initial compression. At 45 mm deflection, so that is maximum compression of the spring. Initial plus maximum lift, that is 45. At 45 mm, so what is the load? The load acting on the valve when it's compressed up to 45 mm. So that load need to calculate. So calculate here 45 into 3094 divided by 35. So that step here written. So here obtained load is 4,364 newtons. You know wall stress factor empirical relation. So that is K is equal to 4C minus 1 by 4C minus 1 by 4C minus 4 plus 0.615 upon C. C is the spring index. So already you know the spring index is, it is the ratio of mean coil diameter to wire diameter. So for C already given spring index in our problem 5. So substitute in this relation and find the wall stress factor. Once you know the wall stress factor, you can calculate the maximum shear stress. Apply the maximum shear stress formula. The maximum shear stress is, the shear stress is equal to K into AWC by pi d square. So here written the shear stress in our problem given 500 megapascal. So that is 500 Newton for mm square. So substitute that shear stress value in this relation, and here already we calculated here K value in known value and W load, that is maximum load at maximum deflection 45 mm 4364 and C is 5 and pi d square. Here D is wide diameter unknown. We don't know this wide diameter. We need to calculate the wide diameter. Clear? So find out D. So the D is 12.06 mm. So this value you can take from the standard values, the design data book as per SWG 12.7. So refer the design data book and fix the standard value diameter of the spring coil. The next one is mean coil diameter. So once you know calculated this diameter of spring wire, then easily you can you may fix mean coil diameter. Why? Because here already you know the spring index value C. So spring index is equal to mean coil diameter upon wire diameter. It is the ratio of mean coil diameter to wire diameter. So already here written. So by using this relation, you may calculate mean coil diameter. So the mean coil diameter is C into D. So 63.5 mm. Similarly, the number of active turns. Let N is equal to number of active turns. So using this deflection relation, maximum compression, so that is delta is AW CQ N by G into D. Clear? So this equation you may written like this also, AW into capital D upon by small d Q into N by G into D. So again, no need to calculate D by D every time. Why? Because already we have this C spring index value. So directly substitute. So but here unknown is N, number of active turns. So find out N number of active turns here. You got 11. So actually 10.5, you can say 11 turns. So here ends, taking the ends of the coil as a squared and ground. So not given in your problem. So generally the helical coil springs are, the end conditions are squares, ground and squared shape. So the total number of turns depends upon this end conditions of the spring. So here assume ground and squared, so that for this condition, for this end condition, total number of turns is equal to n plus 2. Here n is active turns and n dash is the total number of turns. So while applying load, so all turns are not inactive. Some turns are active and another. So remaining turns are inactive. It may not deflect up to the portion of the bottom portion of the spring. So that you need to calculate total number of turns by using end conditions of the spring and total number of active turns. So here active turns are already calculated in a previous step, 11 plus 2. So total 13. Out of 13 turns, only 11 turns are active. Remaining 2 turns are inactive. So it may not absorb any energy. So here calculated total number of turns are 13, and then the valve of n may also be calculated by using another relation is there. So here also we got 11. So W1 initial, this is for maximum load. This is for load at 35 mm compression of the spring. This is at wall spring. Wall spring initial compression. Initial compression is 35. The maximum is 10. And then the total compression of the spring is 45. So in previous step we have calculated at 45. Here calculated at 35. Okay. Like this, you have to calculate the spring problem for the given application. So fourth one is pitch of the coil. Here you know that the free length of the spring is n dash into d plus delta max plus 0.15 delta max. So n dash, total number of turns multiplied with d, y diameter, and delta maximum, that is the total compression of the spring, taken 45 and multiply with 0.15. So you will get 216.85. So that from this value you may calculate pitch of the coil free length upon n dash minus 1. So while calculating pitch of the coil, always use free length of the spring only. Two types of lengths are there already, you know, we have discussed in definitions. So one is solid length and another one is free length. So here you must take the free length. Pitch of the coil is equal to free length upon n dash minus 1. So total the pitch is 18.1. So one more problem we will see. The second problem. Here given spring is closely coiled helical spring. They made of 10 mm diameter steel wire. So here wire diameter is given. The coil consisting of 10 complete turns also given. So another model, this one. With a mean diameter of 120 mm. So mean coil diameter also given 120 mm. The spring carries an axial pull of 200 newtons. So here axial load is 200 newtons. Determine the shear stress induced in the spring, neglecting the effect of stress concentration. Here, neglecting the effect of stress concentration. No need to take all factors. So shear stress need to calculate, not given. Also determine the deflection of the spring delta, its stiffness and strain energy stored by it if the modulus of rigidity value given 80 kilonewton modulus of rigidity 80 kilonewton for mm square kilonewton per mm square. So now write down the given data. Given data is D is equal to 10 mm and N is 10 and capital D. This is capital D is mean coil diameter, mean coil dia, and small d is wide dia, and W is the load, and 80 is the 80 kilonewton per mm square is modulus of rigidity. So shear stress induced in the spring, neglecting the effect of stress concentration. So what is the formula? So the formula is shear stress is equal to 8WD upon pi d cube multiplied with 1 plus small d by 2d. Here all values known values. So here except shear stress we know load and mean coil diameter and wide diameter. So substitute those values in this equation. So substitute W. Here given W is 200 newtons and then capital D mean coil diameter 120, small d 10. So calculate after simplification. So you will get 63.454 megapascal. So you can convert into Newton per mm square, that same 63.54 Newton per mm square. 1 megapascal is equal to 1 Newton per mm square. 1 MPa is equal to 1 Newton per mm square. So deflection in the spring. So we calculate the deflection. The deflection formula already you know. This deflection is equal to AW dq into n by g into d to the power of 4. You may write in another way also. AW here in place of dq d by d square dq by small dq into n divided by g d. So here in place of d by d you may write c. C is equal to capital D by small d. Clear? So you can substitute the C value in this. But C directly not given. So need to calculate again by using this mean coil diameter and wide diameter. Spring index is nothing but it is the ratio of mean coil diameter to wide diameter. So here capital D by D, the D is mean coil diameter is 200 and small g is 10. So here 20. The spring index is 20. So you may calculate like this also. So you will get 34.56 mm. Next calculate the stiffness of the spring. The stiffness of the spring is load for unit deflection. So deflection calculated in a previous step. So that is 34.56. The stiffness of the spring is load upon deflection. So here load is 200 and deflection is 34.56. So 5.8 Newton per mm. The unit load per unit deflection. Next one is strain energy stored in the spring. The strain energy is half into W into delta. So apply this relation. So calculate, you will get 3.456 Newton meter. So next problem, third problem, we will see rail wagon problem. So the spring is here. The application of spring is for a rail wagon. So the rail wagon of mass 20 tons is moving with a velocity of 2 meters per second. It is brought to rest by two buffers with springs of 300 mm diameter. The diameter of the springs, two buffers with springs, the spring diameter is 300 mm. The maximum deflection of springs is 250 mm. The maximum deflection of the spring is 250 mm. The allowable shear stress in the spring material is 600 mm, 600 megapascal. Shear stress given. Tau. So what he has asked, design the spring for the buffers. Here, for rail wagon, two buffers are used with springs. What is the diameter? 300 mm diameter each. So they can deflect up to 250 mm. For what purpose? The rail wagon is brought to rest. So what is the mass of the rail wagon? 20 tons. The moving velocity is 2 meters per second. So how to design the spring for the buffers? So in this problem I will explain. Given data, 20 tons, convert into kgs, mass of the rail wagon, velocity 2 meters per second, the mean coil diameter 300 mm, delta given 250 mm, shear stress 600 megapascal, 600 Newton per mm square, convert into Newton per mm square. So first diameter of the spring wire. So wire diameter, how do you calculate? By using kinetic energy of the rail wagon. So how do you calculate the kinetic energy of the rail wagon? Half into mv square. Mass available and velocity also available. Calculate the kinetic energy of the wagon. So the kinetic energy is half multiply with mass 20,000 multiply with velocity square. So the velocity is 2 meters per second. So 40 into 10 to the power of 6 Newton mm will get energy, kinetic energy of the wagon. So here, let's take W with the equivalent load. When applied a load on each spring, the deflection is 250 mm. See here given springs are two springs. Therefore, the energy stored in the spring, is half into W into delta into 2. So this is energy, strain energy, U. For single spring, U is equal to half W into delta. But here given number of springs are 2. So multiply with 2 shown in this equation. From equation 1 and 2, you may calculate W. In previous session, W here, the kinetic energy of the wagon is 40 into 10 kilonewton, 10 to the power of 6. And here, this energy is, you will get in terms of W 250 W Newton mm. So this energy is equal to, the energy stored in the spring is equal to the kinetic energy of the rail wagon. See here, whatever you calculated in the previous step. So this how much energy stored in the spring is equal to the kinetic energy of the spring rail wagon. So that you will get the W is 160 to 10 to the power of cube 3 newtons. 10 cube newtons. So here torque transmitted by the spring. The torque transmitted by the spring T is equal to W into the radius, that is D by 2. D by 2. So here W calculated, the equivalent load applied on E spring W multiply with radius, that distance, that is D by 2. Here mean coil diameter 300 mm by 2, you will get 24 into 10 to the power of 6 Newton mm. So you know the torque transmitted by the spring. So you may calculate the shear stress. So here the torque transmitted by the spring T is equal to this equation already you know, T is equal to 5 by 16 into tau into dq. So here tau is the shear stress and D is the Y diameter. So this is unknown, Y diameter we don't know. So torque already calculated and the shear stress also given in the problem. So substitute the given values and then find D. So here torque is 24 into 10 to the power of 6 and 5 by 16 into tau into dq. Here tau value 600 mm and D is the Y diameter. So you will get in terms of D 117.8 dq. So finally the diameter is 58.8. You can say 60 mm the diameter of Y diameter. The final Y diameter is 60 mm. Clear? So like this how to design. Next one is number of turns of the spring coil. So first step is completed. Mean diameter already given and the Y diameter unknown. So Y diameter calculated. Next need to calculate the number of turns of the spring coil and then free length and pitch of the coil. So then only your design will be completed. So number of turns of the spring. So here in this turns, some turns are active, remaining turns are inactive. So need to calculate both the total number of turns. So the total number of turns depends upon the end conditions of the spring. So let's take n number of active turns of the spring coil. So deflection is D is delta is equal to AW dq by G d to the power of 4 into n. So W already calculated, D known value and small d also calculated in your first step, Y diameter, n we don't know. So n is here unknown. So substitute those values and calculate n. N is 8. Assume here The end conditions of the spring is square and ground ends. For square and ground ends, the end conditions n dash is the total number of turns are n dash is equal to n plus 2. Here n is active turns of the spring. Clear? So total number of turns as per assumed condition square and ground n plus 2. N is 8, 8 plus 2, total 10. So now free length of the spring you can calculate. So free length of the spring is n dash d plus delta plus 0.15 delta. So delta max is here 250. The maximum deflection 250. So 250 multiply with 0.15 and 10 multiply with 60 plus 250. So delta already calculated and given in our problem, delta is 250. Clear? So that you will get free length of the spring is 887.5. The fourth point is pitch of the coil. So by using this free length of the spring value, you may calculate the pitch of the coil. Pitch of the coil is equal to free length upon n dash minus 1. So free length calculated as 887.5 and n dash minus 1. N dash is total number of turns are 10. 10 minus 1, 9. So calculate here 98.6 will get the pitch of the coil. So like this you have to calculate one by one according to the given condition. So next fourth problem we will see. This problem is for a helical torsion spring. Up to now we have seen helical closely coiled helical spring, and in this problem we will see the helical torsion spring of mean diameter is 60 mm. The made of round wire is 6 mm diameter. So wire diameter given and capital D also given. If a torque of 6 Newton meter is applied on the spring, so here torque applied. So because this type of spring is a torsion spring, find the bending stress induced and the angular deflection of the spring in degrees. So what is the angular deflection, that is theta in spring in degrees, and the bending stress. The spring index is 10 and the modulus of elasticity for the spring material is 200 kilonewton per mm square. The number of effective turns may be taken as 5.5. The effective turns, so active turns. So here mean coil diameter, given data. First write down the given data. Given capital D 60 mm and wire diameter, that is small d 6 mm. If a torque of 6 newtons is applied on the spring, so the torque is 6 Newton meter. Find the bending stress. So bending stress we don't know. And angular deflection, that is theta in spring in degrees. The spring index is 10. The C value is given 10. And the modulus of velocity for the spring material is capital E is 200 kilonewton per mm square. The number of active turns may be taken as n is 5.5 given. So now we will see problem solution, how to solve the given problem. Given data is over, and here the bending stress induced. So we know that the wall stress factor for a spring made of round wire. So find out the wall stress factor. For the On torsional spring, the wall stress factor relation is K is equal to 4C square minus C minus 1 by 4C square minus 4C. For a helical compression spring, so already you know the K is equal to 4C minus 1 by 4C minus 4 plus 0.615 by 4C. Clear? So this is for a helical spring. And given spring is here in this problem, torsional spring. So that's why I apply this wall stress factor. So bending stress induced is B is equal to K multiplied with 32 M by pi d cube. Sigma B. So actually the general formula sigma B, the bending moment is equal to 5 by 32 into d cube into sigma B. So here for bending stress induced in terms of wall stress factor for springs problem. So this is for shafts and circular cross section of objects. This K multiply with 32 M by pi d cube. So there bending moment is 6000 in Newton, 6 Newton meter. So that is 6000 Newton mm. And then d small d y diameter given. So you will get 305.5 Newton mm square or megapascal. So the angular deflection of the spring theta you may calculate by using this relation 64 m into d into n upon e into d to the power 4. Here n is total active turns. So effective turns are given here n 5.5. M already known value, and d known, all values are given. So substitute and find out the angular deflection of the spring in terms of degrees. So you may get here 28 degrees. So here number of effective turns are given. No need to calculate the total number of turns in this case of torsional spring. So like this, you need to calculate all values of a torsional spring. I have taken references like this, V. Bhandari. So this is a textbook of design of machine elements, and R.S. Kurmi, and one more book is there, R.L. Norton. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.